Hi, in this video, we'll be talking more about vectors. And so, let's begin with understanding what is known as a vector projection of U. So, for example, now we have two vectors U and V, and we want to find the component that U is parallel to V. And so this is known as a vector projection. And so what we really think about is we have this vector U and we project it onto a line parallel to V. And how do we find this vector? Well, we know that this length is actually, if you draw a triangle, it's U cosine theta. And so, how to find a vector is always with a length and a direction. And so you just need to take U cosine theta multiplied with the unit vector representing V. And you realize that U cosine theta is actually U dot V over the length of V, because U dot the unit vector will equals to U times the length of the unit vector, which actually equals 1 cosine theta. So it simplifies to U cosine theta. And you can see it over here. So now it reduces to this. So the projection vector actually is U dot V over V squared times V. And if the cos angle is acute, then it is parallel. And if it's obtuse, then it's in the opposite direction of V. And the scalar component is really just U cosine theta, which is U dot V over the length of V. And let's just prove some properties to understand this projection vector. Is that U minus the projection is actually always orthogonal to the projection vector. And really, you just need to dot it and verify that equals to 0. And so, you can think of U now equals to the projection vector plus some component perpendicular to the projection vector. So you can always break up the vector U into a vector parallel to another vector that you want and orthogonal to V. And this is really quite a useful property, because if you think of it as a force, the force acting perpendicular will not do anything to this direction. And so what's the effective force? It is the one parallel to the direction vector of V. Another definition to note is this thing known as the direction cosine, and it's really just the angle you make with respect to the x, y, and z axis. And so you're really multiplying, you're finding the angle it makes with the vector I, the vector j, and the vector k, the standard Euclidean basis. And so it simplifies out to be the component of your vector, the first component divided by the total length. For the y, it's just a2, and for the z, it's a3 over the length of a. And lastly, the last operation we can define of three-dimensional vectors, which is only applicable for three-dimensional vectors, is known as the cross product. And the cross product is really defined to be this a2b3 minus a3b2, a3b1 minus a1b3, a1b2 minus a2b1. And you realize that this can be written as a determinant of this matrix ijk a1 a2 a3 as the second row, and the b vector as the third row. Because when you simplify this, when you expand this along the first row, then you get this, which equals to this. And we'll see later geometrically what does this cross product represent, and by doing so, what can it give us. And so this is a good definition. So this is a simple example for you to practice computation of the cross product. And you can actually take a look at all these properties that it has. That I times j is k, j times k is I, and k times I is j. And if you multiply by a vector equal to yourself, then you're equals to 0. And more generally, we'll see what it means later on. So some properties is that it's anti-commutative. So when I say A cross with B, the second row really must be A, the first one, and the third row is the second one. So the first row must be A and the second row must be B. Because A cross B equals to, if you switch it around, B cross A equals to negative A cross B. It's also distributive. And so the vector A, and you must also note that A cross B gives you a vector in the end. So you can see that it's in the components of I, J, and K. So this is a vector. And so this vector now is orthogonal to both A and B. And so you can show that by multiplying the dot product and see that equals to 0. Meaning the angle between it makes with A and B is 0. And really this means that the vector points in a direction perpendicular to the plane spanned by A and B. And if you want to find the how it points, whether it's up or down, then you just need to take the right hand rule where we curl our fingers going from the vector A to the vector B. And geometrically, we can think of A cross B or U cross V as U, the length of U times the length of V times sine theta times a normal vector perpendicular to A and B. And this normal vector is a unit vector. And for this, you just need to work out, and you can prove this from using the dot product formula of A dot B equals to the length of A and the length of B cosine theta. And you really work it out and you can expand out to get this formula. And because of this proposition, that you get a second definition for the cross product in terms of sine theta, you can see that it actually represents the area of the parallelogram determined by A and B from this picture over here. Because now the height of the parallelogram is actually B sine theta. And also, from this geometric understanding, you can see that if A and B are parallel, if and only if the cross product equals to 0. So if this is 0, it means sine theta is 0, meaning theta equals to 0. And so A and B are parallel. And lastly, we like to note that there's this thing known as the scalar triple product, where you take A and you dot it with the vector B cross C. And really, it reduces to finding the determinant of A1, A2, A3, B's as the second row and C's as the third row. And what it represents is that it represents the volume of the parallel pipe. Because B cross C is the area of the parallelogram. And then when you dot it with the vector A, your A is just, you get the height A cosine theta when you take it with respect to the normal vector of this plane. And so you can really work out the formula and see that it really represents this volume of the parallel pipe, because you get the perpendicular height multiplied by base area. So please try out more examples in the textbook that we are using, Thomas Calculus, and I'll catch you in the next video. Bye!